Hey there and welcome. Have you ever felt like math has its own secret language? I mean, with all the theorems, proofs, and axioms, it can feel a little intimidating, right? Well, you're not wrong. It does have its own language. And today, we're going to crack that code. We're going to make sense of how mathematicians build their incredible world of logic and certainty. Okay, so let me set the scene for you. It's a classic story, almost a legend in the math world. A teacher, probably just wanting a few minutes of peace and quiet, gives his class this impossible task. He tells them to add up every single number, all the way from 1 to 100. But then, this one young student, a kid named Carl Friedrich Gauss, pipes up with the answer almost instantly. We're talking seconds. So, how on earth did he do it? No, he wasn't some human calculator. He did something much, much cooler. He saw a hidden structure. This beautiful, elegant pattern that just unlocked the whole thing. He turned a super tedious problem into a simple, beautiful solution. And that, right there, that moment of insight, that is the heart and soul of mathematics. It's not just about crunching numbers. It's about seeing the patterns. And that's exactly what we're diving into today. Now, our guide for this whole journey comes from a really great article called Math Terms Made Simple, written by Mukesh Tekwani over on scitechgen.com. So big thanks to Mukesh for laying this all out so clearly. We're basically using his article as our blueprint to understand all these powerful ideas. All right, let's start with a little analogy. I want you to think of mathematics like you're building a massive, incredible skyscraper. Before you can even think about putting up walls or windows, you need two absolutely essential things, right? You need a rock-solid foundation, and you need a crystal clear set of blueprints. So, let's talk about that foundation first. In the world of math, we call this an axiom. And an axiom is just a basic rule, something so obvious that we all just agree it's true. We don't need to prove it, it's just a given. Think of it as the bedrock, the solid ground we all have to stand on before we can start building anything else. And what's really cool is how intuitive these things are. You already know this stuff. Like, through any 2 points, there's one straight line. Yeah, of course. Or a plus b equals b plus a. 2 plus 3 is the same as 3 plus 2. These aren't some weird, complicated rules you have to memorize. They're just the fundamental starting points of the entire game of math. Okay, so our foundation is poured, we've got our axioms, now we need the blueprints. And in math, our blueprints are the definitions. Now, these aren't like dictionary definitions that can be a little fuzzy. A mathematical definition has to be perfectly precise. There can be zero room for confusion. It's so that when one mathematician says even number in Tokyo, another one in Toronto knows exactly what they're talking about. Let's take a super simple example. The definition of an even number. It's not just a vague idea, it's a super clear test. An integer n is even if, and only if, you can write it as 2 times some other integer k. So is 10 even? Yep, because it's 2 times 5. Is 7 even? Nope, no way. It's a simple yes or no. And that kind of absolute precision, that's everything in math. All right, so we've got our foundation, the axioms. We've got our blueprints, the definitions. Now we can finally start building. So let's talk about the goal of all this construction. What are we trying to build? We're trying to build the landmark results, the big ideas that completely change how we see the world. And that brings us to the theorem. A theorem is like the grand prize, the heavyweight champion of mathematics. It's a huge, significant statement that has been proven to be true beyond any shadow of a doubt. If we're sticking with our city analogy, theorems aren't just buildings, they are the towering skyscrapers that define the skyline. I mean, just think about this for a second. One of the most famous theorems of all time, the Pythagorean Theorem, a squared plus b squared equals c squared, that thing was known over 2,500 years ago. That's not just some formula you memorize for a test. It's an eternal truth. It was true then, it's true now, and it's fundamental to everything from building a house to sending a rover to Mars. That's the incredible power of a theorem. But here's a key thing to remember. Not all true statements are created equal. They don't all carry the same weight. And this is where we see the difference between a big, flashy theorem and a more modest but still useful true statement called a proposition. A theorem, like the Pythagorean theorem, is a total game changer. It unlocks whole new worlds of understanding. A proposition like, say, the sum of 2 even numbers is always even, well, that's true and it's definitely useful, but it's not exactly going to make front page news, Okay, so we know what a theorem is. It's this huge, proven result. But that brings up the next obvious question, right? How in the world do you actually prove one? How do mathematicians build an argument that is so airtight, so logical, that it establishes something as a truth forever? Well, they do it with a proof. And a proof is so much more than just showing your work. It's the entire journey. It's this beautiful, rigorous, step-by-step chain of logic where every single link is forged from those axioms and definitions we talked about earlier. A good proof leaves absolutely no room for doubt. It's not an opinion, it's not a guess, it is a logical demonstration of truth. Now, sometimes proving a huge theorem is, well, it's a really big job. It's too big to do in one giant leap. And that's where a handy little tool called a lemma comes in. I like to think of a lemma as a mini theorem or a helping theorem. It's a smaller result that you prove along the way. It's like putting up some scaffolding before you try to build the top floor. It just makes the main job so much easier. So if you put it all together, you can see the whole journey to a theorem. You start with your solid foundation, the axioms and definitions. Then you put up your scaffolding by proving a helpful lemma or two. With that support in place, you begin the main construction, which is building that step-by-step logical proof. And finally, completion. You've done it. You've established a brand new, magnificent theorem. So imagine you've done it. You've proven a theorem. Congratulations! But what happens next? What's the view like from the top of this amazing new structure you've built? And where do you go from here? Well, one of the first things you often get is something called a corollary. And a corollary is awesome. It's like a buy one, get one free deal in math. It's another true statement that just kind of falls right into your lap after you've done the hard work of proving the theorem. It takes little or no extra proof. It's just an obvious consequence of the big thing you just figured out. Let's go back to our old friend, the Pythagorean Theorem. Because we know a squared plus b squared equals c squared is true for right triangles, we get a corollary for free. We immediately know that a triangle with sides 3, 4, and 6 cannot possibly have a right angle. Why? Simple. Does 3 squared plus 4 squared equal 6 squared? Let's see. 9 plus 16 is 25. That is not 36. So, nope, not a right triangle. See? It's a direct consequence. But here's what keeps math so exciting. Not everything is known. The world of proven theorems is like the mapped territory, the solid ground we've already claimed. But way out on the horizon, at the edge of the map, lies the mysterious and thrilling world of the conjecture. A conjecture is a statement that everyone believes is true. I mean, we might have mountains of evidence suggesting it's true, but no one has ever been able to actually prove it. And we're talking about some of the most famous unsolved problems in all of history here. Take Goldbach's conjecture. It says every even number bigger than 2 is the sum of 2 prime numbers. We've checked it for ridiculously huge numbers, and it always works. 8 is 3 plus 5, 20 is 7 plus 13. But has anyone proven it work for every single even number out to infinity? Nope, not yet. This is the real frontier. This is where the mathematical adventurers are exploring today. Wow, okay, we have covered a lot of ground, from the absolute foundations of math all the way out to the unexplored frontiers. So let's bring it all home with a quick recap, a little reference guide that puts our entire mathematical toolkit in one handy place. So here it is, the whole shebang. You've got your axiom, the basic rule you just assume is true, your definition, the crystal clear meaning of a word, the lemma, your helpful little sidekick, the proof, the logical steps that show something is true, and that leads to the big one, the theorem, the major proven statement. And from that, you get the corollary, the easy bonus prize, and other propositions. And out there on the horizon, the conjecture, the guess we're all trying to prove. That right there is the language of math. Look, at the end of the day, these words aren't just vocabulary you have to memorize. There's so much more than that. They are literally the keys to a kingdom of logic, creativity, and discovery. They describe the process of how we as humans build absolute, certain, eternal knowledge. And now you have those keys. So the only question left is, what are you going to unlock with them?